The Dirac delta and the convolution have some interesting properties that sort of fit together to make a bigger picture involving the delta, convolution, and Laplace transforms. So let's look at a few of those properties. The first one is called the sifting property of the Dirac delta. And the sifting property is that the integral from t1 to t2 of f of tau times Dirac delta of t minus tau d tau is equal to f of t as long as t is in the interval that we're integrating over, so in the interval from t1 to t2. Also, we're going to assume that f is continuous. Okay, so to get an idea of why this is the case, let's remember that if we have some question about exactly how the Dirac delta behaves, we should replace it with a limit as a goes to 0 of Dirac delta sub a, so of t minus tau d tau. Now remember that delta sub a, so on our horizontal axis, and then we're going to graph delta sub a. Remember, delta sub a is this spike that has width 2a and height 1 over 2a, so that the area under this graph is always 1, even as a goes towards 0. And as a goes towards 0, this spike gets narrower and taller, right? So if f is continuous and a is small, since a is going to 0, let's imagine what happens to this product. Well, first of all, since it's delta sub a of t minus tau, when it's shifted, this spike is centered at t instead of at 0. So this part here is a tall spike at t, right? And since f of t is continuous, we have this very tall spike, right? We're multiplying f of tau by this very tall spike at t. So what happens? Well, the only value of f that matters here is the value at t, because that's where the spike is, right? If you're at a tau value far away from t, then this delta sub a is 0, and so the integrand gets zeroed out. So for t values near for tau values near t, f of tau is essentially approximately f of t. And this approximation gets better and better as a goes to 0. So I guess we need to write down our limit as a goes to 0 times delta sub a of t minus tau d tau. Okay, but now this f of t doesn't depend on tau anymore, so we can move it outside of the integral, and we can also move it outside of the limit. So it's f of t. So a is going to 0. Integral from t1 to t2 of delta sub a of t minus tau d tau. So f of t times, but this integral, right, this is just the area under this spike, but we set up this spike delta sub a so that the area under that spike is always 1, no matter what a is. So this is just f of t times 1, but that's f of t, right? So if you'll allow me this approximation here, then we've demonstrated that integrating against a shifted delta essentially selects that value of the function. You can make this approximation perfectly precise with a squeeze theorem type limiting argument. So the sifting property is the first interesting property of the Dirac delta. Let's look at some properties of the convolution. So the first property I want to look at is that the convolution is actually it's a commutative operation. It doesn't matter which order you do the convolution, f convolve g or g convolve f. So to see that this is the case, let's start with f convolve g. So by definition, this is the integral from 0 to t of f of tau times g of t minus tau d tau. And what we're going to do is introduce a new variable called u, and u is going to be t minus tau. So du is minus d tau, and tau, in terms of u, right, if you move these over, tau is t minus u. Okay, so now let's do this change of variables in our integral. So when tau is 0, right, this bottom bound here is a tau value, so is this top bound. At the bottom bound, when tau is 0, u is t. And at the top bound, when tau is t, u is 0. Okay, f of tau, but in terms of u, tau is t minus u times g of t minus tau, but that's u, and dt is minus du. Okay, well, we can use this minus sign here to turn this, switch the order of the bounds here. So this is integral from 0 to t. Also, while I'm at it, I'm going to write the f over there and the g over there. So g of u times f of u minus tau. I made a mistake here. This should be, no, this is, I'm sorry, this is right. T minus u du. But if you look at this final expression, this is exactly the integral that gives you g convolve f. The only difference is u is the variable for the integral instead of tau, but right, this variable for the integral is a dummy variable. It doesn't matter what variable you use there. So the fact that it's u instead of tau doesn't matter. So this shows that f convolve g is equal to g convolve f. All right, second interesting property of the convolution is that f convolve delta is actually the same as f. So let's see why that is. So f convolve delta is the integral from 0 to t of f of tau times delta of t minus tau d tau. And now we can use the sifting property. Since the t value that we're shifting is in the interval of integration, the sifting property says that this integral is just f of t. And so we're done. F convolve delta is just f. So this is sort of strange. This is saying that delta actually acts like a unit or an identity for the convolution operation. So it's not, right, it's sort of, it might be your initial guess that f convolve 1 is f, but that's not true. It's f convolve delta that's equal to f. Okay, final property of convolution is how it interacts with the derivative. So what's the derivative of a convolution? Well, it turns out it's some initial values here plus a f convolve the derivative of g. So let's see why this is. So we need to take the derivative with respect to t of f convolve g. And f convolve g is the integral from 0 to t of f of tau times g of t minus tau d tau. And now we need to work out this derivative. And so you have to be a little careful. You have to actually know some multivariable calculus to see how this works out, because t shows up in two places. It shows up here, and it shows up here. So first we need to take the derivative of this thing inside with respect to that position. But the fundamental theorem of calculus says that that is f of t times g of t minus t, which is 0. And then we have to multiply by the derivative of whatever shows up inside this red box, which is t, with respect to the variable that we're differentiating with respect to, which is t. So dt dt, that's 1. Okay, plus, and now we have to differentiate this whole thing with respect to this second position. So this is integral from 0 to t of f of tau times the derivative with respect to t of g of t minus tau d tau. And then we have to multiply by the derivative with respect to t of whatever shows up in this second box, but that's t, and dt dt is 1 again. Okay, so f of t times g of 0 plus the integral from 0 to t of f of tau times, now we need to take the derivative with respect to t of g of t minus tau, but that's g prime, or g dt, evaluated at t minus tau, times dt dt again, but dt dt is 1. And so we're integrating with respect to tau. And so now you see this is f of t times g of 0 plus this expression here, this integral, is exactly the convolution of f and dg dt. So this is sort of an important property because it says if you want to differentiate a convolution, you can just differentiate the second factor, or in fact the first factor since it's commutative. The only delicate point is that you do get this extra term f of t times g of 0. But what we're going to see is in situations where we actually want to differentiate a convolution, one of these two things is going to be 0. And so in sort of the important applications of this formula, the derivative of a convolution is just f convolved with the derivative of g.